So the three techniques that we're going to look at is a homogeneous differential equation, or homogeneous functions, differential equations with homogeneous functions. We're going to take a look at this other type of differential equation called a Bernoulli differential equation. And then we're going to have a special type of differential equation where we're going to perform a substitution based on the type of an expression that we're gonna take and then take the derivative of. So these substitutions would be similar to a U substitution type of technique where you're going to need to compensate for the differentials. And so we're going to take derivatives of things, and then we have to know, the basic derivative rules, the product rule and chain rule, and kind of like the rules for implicit differentiation would be important for us to be able to use. Let's start with the first one. The first one is called the homogeneous differential equation. Not a homogeneous differential equation. I need to keep correcting that. It's a differential equation that contains homogeneous functions. So here's a definition of homogeneous. A function has the property where you replace the x and the y with tx and ty, respectively. Then you would be able to factor out of that function, factor out a t to some alpha. So it looks like the powers of x and y have to match somehow for this to work. So if you satisfy that particular property, then you have what's called a homogeneous function. Now, we wrote our differential equation as m times dx and n times dy. Remember when we were dealing with exact equations? So if your function of m and n are homogeneous functions, and not only are they homogeneous, but they're homogeneous with the same degree, then we can apply this special technique of some sort of substitution. So there's two ways to approach a substitution. One is to replace the y with u times x, or the other one is to replace the x with v times y. And sometimes, most of the time, one is easier than the other. And I don't know of any actual procedures or ways to look at this to make sure you choose the right one from the beginning. So it might be the case where you choose one of them, you go through the process, and then it looks like your differential equation gets a lot harder. Then you have to go back and try the other way, because that might be easier. But I think in either case, you should be able to solve for it. All right. So here are some examples. I propose we do two of them. I'll do the first one, and we'll decide on which one to do next. The first thing we want to check is we want to make sure that it's homogeneous. So let's check that these functions are homogeneous and they're homogeneous of the same degree. So let's get started with an example. So let's start off by writing this function m, and we want to check if that's actually homogeneous. So let's put tx in for x and ty in for y. So we put ty in for y and tx in for x, and then we're gonna massage it a little bit. My teachers used to say that. And then after we work it all out, it looks like it's just t squared times the original m function, right? So here we have a homogeneous function m. So let's try to figure out if n is also homogeneous. So I'll skip a little bit more steps here. Because it's a simpler function. But we see that it's also homogeneous. And not only that, it's homogeneous with the same power. Okay, so that's what we want. We're going to need a lot more room than this. Are we good so far? Okay, now let's make the substitution. Let's let u, or let's let y equal u times x. So I can clearly see where there's a y there. I can just replace the y. But there's one more thing that I need to replace here. And what's that? I need to replace the y. So I can replace all the stuff with a y in it with u times y. But I also have to consider what dy is equal to and replace that. So that means I need an expression for dy. Now what we're dealing with here are functions of x. Right? Y is a function of x. X, well, x is just x is the variable. So when I look at u times x, I'm looking at u as a possible function of x as well. And so I need to find a differential of this. Actually, let's just think about doing differentials. And so when we do the differentials, we do the product rule. And the differential here is going to be the u times the derivative of the second plus the second times the derivative of the first. So we need to make this substitution for the dy. Okay. Now, just like in calc, in u substitution, when you make your substitution, you need to get rid of all the y's or all the u's or all the x's or something, whatever. But here we want to get rid of all the y's, and so all those things that are highlighted are going to get replaced with something with an x and a u, and then we're going to have a differential equation in u. So let's do the substitution. We got u times x quantity squared plus u times x dx. So all the y's that need to be replaced are getting replaced. minus x squared. And now my dy gets replaced with u dx plus x du. Doesn't look easier. So those are the highlighted terms from before that get replaced with our substitution. It's supposed to be easier. Let's see if we can work it out and see if we can eventually solve for this. We have ux squared plus u times x squared dx. Now we need to distribute. Here we have x squared u dx plus x cubed du is equal to 0. Does that look right? Yeah. You mean at this step or the step before? Oh, so this is m, and this is n. And then, so I just consider them as m and n when I'm trying to find out if they're homogeneous. Once I figure out that they're homogeneous, I do this substitution right here. That's my substitution. And then from there, I replace all the y's with the y. And I replace all the dy's, the one dy, with the dy. Josh? The m, when you replace x with tx and y with ty, becomes something with a t times the m function. And then we did the same thing for the n, and we saw that that same t, the same power times n. So these two are homogeneous of the same degree. And then now that we've checked that they're homogeneous, so this little check over here tells us both m and n are homogeneous. If they're different degrees, then this whole technique that begins here, this is the actual technique now, that begins here is you can't do it. Correct. So they have to be both homogeneous, and if they're not, then you have to do something else because this technique isn't going to work. Yes. This substitution? Yeah, it's one or the other. And which one do you pick? I don't think I've gotten to the point where I can tell offhand. And so my deal is to try one, and if it gets really, really difficult to solve, then I'll stop and I'll try the other one. Yeah. The t is nothing anymore after you check if it's homogeneous. That t is just to check whether something's homogeneous or not. And then once we're done with that, we leave the t alone. And then our substitution is all u's or v's, depending on which one you choose. Okay. Well, it's not really a theorem. It's more like a technique. The technique that would help us solve for this differential equation, it's some sort of substitution. Delilah? Well, our function that we're solving for is y. So in the end, at the end of, not the end of the problem, but the end of this technique, we'll be solving for u, and then we'll substitute the y back. Okay? Yes. No, it's a function. So we're replacing it with another function, another variable dependent, and then we're going to treat it as such, so that because that's the substitution. Okay? Yes. Well, the only way you can substitute is that if you know that it's homogeneous. If you're talking about like a test or quiz situation, I'm not going to tell you which technique to use. So what's going to happen is that you're going to get a problem and you have to run down in your head or by paper, is it separable? No. Is it first order linear? No. Then is it homogeneous? No. Is it a Bernoulli? No. And then you have to run down on your own to figure that out. So the idea is practice, practice, practice each of these techniques, and then now start mixing them up, and then figure out which method to use. Okay. All right. Lots of good questions. I hope you're listening to the questions and understanding them. I'm not repeating the questions, so the video is not going to reflect what the questions are. But if anybody's watching the videos, so those are all good questions. Let's continue on with what we're doing here, and then maybe more of the questions can come up after we solve for this. So the idea is to simplify, and this is a good sign that if we start simplifying here, we see a positive u x squared dx and a negative x squared u dx, which means they're going to cancel. And so that simplifies things a little bit for us. And like I said, good news, so that we're dealing with a slightly simpler differential equation that we're trying to solve now. By the way, the differential equation, Delilah's question, the differential equation we're solving for is u as a function of x in this case. So what do we have? We have, let me write this down first, u squared x squared dx. Oh, is that? Minus x cubed du is equal to 0. Is that what you're? Okay, thanks. Is that easier? How do we solve for this? Separable. Nice. So let's put one on the other side. And separate the variables. So let's see. Okay. Let's integrate. And this is an ln x. Uh-oh. Sorry. Hello? Yes. Yeah. Okay. Sorry. Just keep working. What did you do? Can you stay there for another 30 minutes, or can you go back to your class? Okay, just try to go back to class, and then I'll pick you up earlier so you don't have to go to practice. Musical. Where were we? We're solving for u. What's u equal to? So we integrate both sides. Is this right integral, by the way? u to the -2, negative u to the -1. So I put the plus c where the x is, since that's the independent variable. So that's our general rule, is we want to put the plus c next to the independent variable. And then after that, we get our u back, or we get our u and replace that with y over x. And then we can solve for y. I guess, what do we need to do here? Negative x over y equals ln x plus c. And -1 over y. Actually, let's put the negative on the other side also. Ln x plus c divided by -x. And then y equals -x over ln x plus c. Is that right? Yes. More or less. Sorry, Sri. Because just like when you do a regular u substitution, when you're integrating back in Calc 1 and Calc 2, you're treating u as a function of x after you do the substitution. And so that's the same thing over here, because you can't just say let y equal to u, or you can't let u to just be a constant, because y is not constant, y is a function. So we have to assume that u is a function of x, or u is just a function in general, and that we're gonna solve for u. Okay, so when you make these substitutions, when you introduce a new variable, you have to assume that new variable is still going to be a function of something. And so you can't treat it as if it's a constant. Okay? Yeah. T is not related to this at all. T was our tool to check whether something's homogeneous. After we figure that out, we ignore T. It's not part of the problem anymore. Well, what you're saying is that because the function's homogeneous, you can use this technique. If they're not homogeneous, then you cannot use this technique, because it's not going to work. If it's not homogeneous? Oh, if it is homogeneous, then yeah, then we can solve for this, and we can eventually, u is going to be solvable by this substitution. Lyle? Uh-huh. I think eventually you're going to solve for this, and then your answer will be ln x minus c instead of plus c. And minus c plus c is just means they're off by -1. They're off just by another constant. Yeah, so anything times c, a constant times c is still going to be c. So it doesn't matter. No. Oh, are you talking about this? Oh, that's just how the differential equation is written. So the differential equation that's written this way, it's just a differential equation. This may be exact or might not be exact. It depends on the actual function m and n. Yes. 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 Right? So that's your check, right? You're checking on what technique to use. If your differential equation looks like this, the first thing you should check is this an exact equation? So you try to see if it's exact, And if it's not, then I don't want to solve for it using the exact equation way. So you ask yourself, is this homogeneous? Then you would check this. And if it is, then great, this is what you do. And if it's not, then you have to find something else to do. Okay? Any other questions now that we got the answer? You see all the steps that's included for this differential equation? All right, let's try another one. So let's choose. Do you guys want to do number 8 or number 11? Oh, 13. So what? There's no 13. There's no 11. All right. Whoa, man, that looks hard. So here's our differential equation, and we actually have an initial condition. So this is a complete IVP, initial value problem. And the first thing we want to do is we want to check if it's homogeneous. So we identify our M and our N functions, and then check if it's homogeneous. So we put in a Tx and Ty in for X and Y. For the first one, we're going to get a Tx plus Ty times e to the Ty over Tx. So the t's cancel in the exponent, so that's good. That's not going to be an issue. And then we factor out a t, and then we get x plus y e to the y over x. So that is homogeneous with a first degree homogeneous. It's t to the first. So all we did was we just factored out a couple of t's there. So our m is good to go. Let's check our n with a tx and ty. It's just a simple negative x, so that's negative tx. And then we get the same thing for the power, ty over tx. So the t's would cancel again. So this is, in fact, a homogeneous differential equation. So we can move on to actually solve for this using a substitution. All right. So let's try to use the same substitution. Let's try to use the same substitution. Y is equal to, what is it, u times x or something? And then our differential is always going to be the same. Then we substitute a whole bunch of things. So we have our x is just going to be an x. So we only substitute the y's. So we have x plus y, which is u times x, times e to the y over x. So that's u times x over x. So this is a good sign because the x's will cancel, and now we have e to the u power, which is a little bit simpler. simpler to deal with. And then we have a minus x e to the u times x over x again. And then now this is where our differential dy comes in. We have a u dx plus x du. And that whole thing is supposed to be equal to 0. So we can distribute everything, x dx plus u x e to the, I'm just going to put e to the u, right? And then we have a minus x e to the u times u dx. And then here's where I forgot the negative last time. This is going to be x squared e to the u times du. So this is probably about the time where we would figure out whether we made a good substitution or we need to go back and do x is equal to y times v, or v times y. So we cancel and then we say, oh, okay, that's great. So we have an x dx is equal to x squared e to the u du, which is again separable. And it looks like it's going to be similar to what we had before. We have 1 over x dx equals e to the u du. Wonder if I should just go pick up my Okay. Yes.
So is this supposed to be a e to the power of t in there?
No, you just want to make it look like the original function with some factor of t out there. The t times y and t times x as a power would cancel the t's out, and so we kept the same power y over x like we had before. So you don't need an e to the power of t anywhere. Okay? E to the u is equal to ln x plus c. And again, u is equal to y over x. So e to the y over x is equal to ln of x plus c. Now, we can continue to solve for this, or we can try to solve for the c, the unknown variable right now, the constant. So when x is equal to 1, y is equal to 0. So we have e to the 0 over 1 is equal to ln of 1 plus c. So c is equal to 1. So we have e to the y over x is equal to ln x plus 1. And then we can continue to solve for y. Take the ln of both sides. You know what happens when you take the ln of both sides. And then multiply by x, I guess, right? I think the book has an interesting explanation you can try to follow through. Yes.
When we check the homogeneous, I learned from a previous math class that if it's just equal to zero, it's homogeneous. Is that something different, or is
Yeah. So in general, homogeneous systems or homogeneous differential equation means if something's equal to zero. But in this one particular case, this is a homogeneous function, and a homogeneous function satisfies that criteria with t to the alpha. And later on in this class, we're going to see the word homogeneous again, but that is going to be something where it's equal to zero, like you're saying. And so I said this in my linear algebra class yesterday because we started to talk about homogeneous systems of linear equations. And it's unfortunate that this definition is called homogeneous because it sounds like it should be equal to zero, but it's not. I don't know. I think I did. Oh yeah, here it goes. Yeah. So I did suffer. Yes. Yeah, it means it's the same. It's of the same. Well, in this case, it's the same degree, but there's some sort of sameness to it. Um, but yeah, being equal to zero is kind of weird, but that's a term that's used a lot in linear algebra. Now that I think about it, it makes a little bit more sense in this scenario than just setting it equal to zero. But that's how it goes. All right, let's gonna say, you guys okay with this? Well, if you're not, practice. So you can copy the example down in the book, provided that you can get access to the book. Just copy the example down. Don't look at the solutions, and then do it yourself. And then check the solutions to make sure that you got it done correctly. All right, our next technique is dealing with a differential equation that's called a Bernoulli differential equation. Again, this is part of classifying differential equations, whether something's separable or something is an exact differential equation, first order linear, if the functions are homogeneous. Now, another thing to check for is that is a function look like a Bernoulli function, a Bernoulli differential equation. I'm sure these differential equation has some sort of applications to physics, but I don't know off the top of my head. Oh, it's not Bernoulli principle. It's the Bernoulli differential equation. Yeah, it's the same guy. So a lot of those guys came up with a lot of different things that relate to math and physics and stuff. So they're all over the place. Yeah, I would say it's the technique to solve for homogeneous differential equations, and that's too long. So just say homogeneous. And the technique isn't even homogeneous. The homogeneous is just the type of differential equation it is. The technique is actually a substitution where the substitution is y equals u times x, or x is equal to y times v. In fact, this one is also another substitution, and the Bernoulli part of it is just identifying if it's a Bernoulli differential equation. So we look at it, we ask, is this a Bernoulli differential equation? And then the technique, the actual technique, is a substitution. Okay? So Bernoulli differential equation almost looks like it's a linear differential equation, except that there's, on the right-hand side, there's an extra y to some power. Okay? So that extra y to some power means that there's going to be some special trick to solve for this, and the trick is going to be U substitution. I guess I should say technique to solve for this, where you can retransform it to look like a first order linear differential equation. Because like they're saying here, as long as n doesn't equal to 0 or 1, it's not a linear, it's a first order, but it's not a linear differential equation. But a good substitution would make it linear again. And so that's what's going to happen. So our substitution to make it linear is we're going to let u equal to y to the 1 minus n power. Because what happens when you put y minus n over here, then this is just going to be a u, and that's going to be, I don't know what that's going to be, something else. You know, those guys just sit around and think all day. You know, they didn't have lives. That was a lot. So I guess we need to find some examples for this one. Do we have examples? Um, we might as well jump to an initial value problem right away. So let's try to do number 22 or something. All right, so this isn't exactly in the form that we want to be able to read this as something that's a Bernoulli equation, but if we take one step where we clear out the coefficients of dy dx, so let's divide by y to the 1/2 power. So we got y to the 3/2 divided by y to the 1/2. So that's just equal to y is equal to 1 and then y to the negative 1/2 power. So y to the 3/2 divided by y to the 1/2 is like y to the 3/2 minus 1/2. You subtract the powers. Is that what you were thinking? That's what I was thinking. So that's just y. I don't think that'll work because you add powers. So, or what we really want to do is we want to divide by 1/2, which is like multiplying by y to the negative 1/2. So this is, in fact, Bernoulli. It's a nice, simple Bernoulli equation because p of x is equal to 1 and f of x is equal to 1. It's going to make our lives a little bit easier. All right, so we're going to make our substitution. Let's do our substitution. This is Bernoulli, by the way. This is where we decide, yes, it's Bernoulli. And then we move on. So we're going to make our substitution of u is equal to y to the 1 minus, what's n equal to in this case? Negative 1/2, right? So really, our substitution is y is equal to u is equal to y to the 3/2. But I'm not making a u substitution. I mean, I'm making a u substitution, but I need to figure out what y is equal to. So that I can change this problem in terms of u. So what's y equal to? U to the, that's y. And not only that, I have a dy dx. Now remember, when we make these substitutions, we have to assume that these are functions. So I'm assuming that u is a function of x, y is a function of x. And in this case, we could treat this as a function of x instead of implicitly with the differentials and stuff. So if just like a u substitution, except here is like a y substitution at this point, I want to replace the dy dx with something. So what's dy dx equal to if y is equal to this? Assuming u is a function of x, which is what we have to assume whenever we make some sort of substitution, the new variable is going to be a function. Then we're going to need to compensate for those differentials. So here we have an actual derivative dy dx that we need to replace. And so we're going to replace that with something with a du dx. So remember, when we're transforming everything out of y and into u, then everything, including the differentials, the derivatives, have to be in terms of u, the new variable. Okay? Yes? I don't know about that last part. You substitute for constant. If it's independent, not necessarily, because in the homogeneous examples that we have, when you let x equal to yv, then you're assuming that x itself is a variable. They kind of lose their independence at that point, and so you want to treat it just like a regular variable. So the substitution is still v times y, which are still variables. So you have to treat them as variables still. Does that make sense? No constants. I was going to say ever, but let's just say no constant substitutions. Okay, let's see if we can replace these things. We have a dy dx. So back to our differential equations, and we're going to do some replacing here. We're going to replace dy dx with whatever we got for dy dx. We're going to replace the y's with whatever we got for the y's, and we're going to see what we're going to get. So our substitution gives us a 2/3 u to the negative 1/3 power du dx plus y u to the 2/3 is equal to y u to the 2/3 raised to the negative 1/2 power. So I made these substitutions. The dy dx, the y's, and then they're fitting in this. So now I have a differential equation with u and x and no more y's. Okay. Oh, yeah, this one. All right. So now let's look at it in terms as a well, we don't know if it's going to be a linear differential equation. Let's get du dx by itself, or at least divide by the coefficients. And then if I do that, I would divide everything by, or multiply everything by 3/2 u to the 1/3. Is that the correct way to do this? If I want to multiply this whole thing to get rid of this expression, the coefficient of du dx, I would multiply by the reciprocal, and I think this is the reciprocal. Yeah. And so I have 3/2 u to the 2/3 times u to the 1/3. So that's u to the 2/3 plus 1/3. It's u to the first power. Is equal to u to the negative 1/3 times u to the positive 1/3. U to the 0 power. It is first order. It's linear. So it's a first order linear differential equation. Okay? So let's get those bubbles up here. Okay? Yes. Well, we wouldn't want to substitute because now we have a good chance of solving for this. We can solve for this, right? This is a first order linear, and so we would find an integrating factor and be able to solve for it. So quickly, I don't think it's separable. It's the integrating factor is e to the 3/2 x. So this is a first order linear. So this is going to be e to the 3/2 x times u 3/2 e to the 3/2 x, and then you integrate. So this is 3/2. The integral of this is 2/3 e to the 3/2 x plus a constant, and then these things would cancel, and u is going to equal to 1 plus e to the negative 3/2 x times c. Is that time? So you can finish this. We have an initial condition. Initial conditions up here, 0, 4. And then we should, after you get this, you need to get this in terms of y. So you need to substitute back the y and then be able to figure this out. Okay? So see how you do with that. And good luck. It's not separable.